Hi, physics. Mr. Janowski here. This is part 6 of the chapter 13 slides, and this will actually be the last part of the chapter 13 slides. So in the previous part, we talked about gravitational potential energy. We got a new formula for that we have to use when we're dealing with things that can be very far away from their planet, like moons and asteroids and other planets, and things falling out of the Kuiper belt and things like that. And then we got to combine that with the law of conservation of energy, which we learned back in chapter 9, and see how those ideas fit together. So we're going to keep using those ideas from chapter 9 and do some interesting stuff in this one. So in this part of the slides, we will get to one of the biggest, most famous rock stars of all of physics and astronomy too. So it's neat stuff. Let's get started. So what is the new formula for GPE we learned in the last part? It's this one. GPE is equal to minus G M1 M2 over D. And a couple of things to point out real quick. One is this negative sign. You need this negative sign. Under this formula, GPE will always be negative or possibly very, very small and very close to zero, and we'll just call it zero. And the other thing to point out is the right side of this equation looks a whole lot like our formula for force due to gravity. So the only difference is this isn't squared. So make sure you're being careful when you're grabbing these formulas off of the footer and doing the homework problems that you're grabbing the right thing and squaring it if it needs to be squared and not squaring it if it needs not to be squared. So the second question, what happens to the value of GPE when the distance d between the objects gets very large? As d approaches infinity, GPE approaches zero. So if we look back up here, if this starts to get very big, if the denominator starts to get very big, GPE is going to start to get very small. And if you're infinitely far away, infinitely being in scare quotes there, then GPE is going to be zero. And third question, what is the formula for the conservation of energy? This is one of our very big one with everything kind of ideas. Sigma E initial plus sigma work external equals sigma E final. So some of your initial work plus the sum of any external work that's done on the thing will give you the sum of the final work. Now to quickly review, what is Kepler's first law? Kepler's first law is the law of ellipses. So planets don't go around the sun in perfect circles. They actually go around in ellipses, and the sun is at one of the focuses of the ellipse. What is the second law? Kepler's second law is, it's called the law of equal areas. Basically, it's this idea, watch the GIF, that the planet will move slowly when it's far from the sun, and as it gets closer to the sun, it will move faster. Whee! And Kepler's third law, which one is this? This is the law of periods. So this is the one that we can actually do math problems with, so this is the one that I like. So there's a mathematical relationship between the period, which is the length of time, that's why period is a big T, the length of time it takes for a planet to orbit the sun, or this could be a moon orbiting a planet or a satellite orbiting a planet or anything like that. But the length of time it takes for it to orbit, and the relationship is between the mass of the thing that is being orbited. Again, it's important that it's the mass of the thing being orbited, not the mass of the thing doing the orbiting, and r cubed, which is the semi-major axis. It's the longer radius of the ellipse. It's basically the radius. Ellipses aren't circles. They don't actually have radiuses, but it's basically the radius. So those are Kepler's three laws. So what goes up must come down. Not true. We have this idea in physics called escape velocity. So perhaps you've heard of this before. What is escape velocity? Escape velocity is the minimum initial velocity an object needs to completely escape the gravitational attraction of a planet. So this is not the formula for escape velocity. This is the formula for force due to gravity between two masses. But what I want you to notice is, again, that as the distance starts to get big, the force starts to get small. So no matter how far away you are from a planet, that planet is always going to be trying to pull you back. However, as you start to get further and further away, the strength of that force starts to get smaller and smaller. And basically, if you're moving fast enough when you leave, Once you get very far away and the planet is barely pulling on you, if you're still barely moving away, you're not going to go back to the planet. You're not going to come back down. So if the object is moving fast enough, it will never come back. So there's the definition again. Escape velocity is the minimum initial velocity an object needs to completely escape the gravitational attraction of a planet. So a couple of things that we do to kind of simplify this. So when calculating escape velocity, assume that after the object is launched, no negative work is done on the object, so we're going to ignore air resistance. So we're launching something off of the surface of the Earth. It's obviously going to fly through the atmosphere. There's going to be drag, air resistance, but we're going to just completely ignore that because that's how we do these problems. And the other thing we're going to assume is that no positive work is done on the object, which means after this thing is launched, we're not going to do any external work on it. So we're going to pretend like, well, there's not rockets on it firing it and things like that. So let me point out that this is not how rockets are actually launched. When the rocket, it 3, 2, 1 ignition, it goes up. There's rockets pushing on this thing the whole time that it's going up through the Earth's atmosphere. So there is always external work being done on any real rocket that we're going to launch. This would be a lot more like if we had a gigantic cannon and we pointed the cannon straight up and fired it, and as soon as the cannonball or whatever it is we're firing, as soon as it leaves the gun, there's nothing else that we're going to add to it. So there's no rockets pushing on it. This is a lot more, when we do this calculation, we pretend basically like it's a bullet leaving a gun and not a rocket that keeps pushing itself up. So not perfectly realistic in practice. We have gotten things to completely escape Earth's gravitational field. Like the Voyager spacecraft, they're not coming back. And, the other deep space things we've launched, Voyagers, or the 2 Voyagers are the most famous. But we don't actually launch them this way. But it's still an important idea. You'll see why. So what is the minimum initial velocity an object of mass m would need to escape the gravitational attraction of a planet of mass capital M and radius capital R? So the ideas we're going to use here are the law of conservation of energy, our formula for kinetic energy, and our new formula for gravitational potential energy. So I didn't draw the sketches, but just try to imagine what's going on here. So basically, we're launching this thing from the surface of the planet. So it has initial velocity, which means it has initial kinetic energy, and it's near the planet. So we have to assume that there's gravitational potential energy that we have to deal with. We're going to assume there is no external work being done. So there's no rockets pushing this thing up. We literally launched it like we fired a bullet out of a gun. So that's the left side of this. Now, the right side of this, we have to consider the final kinetic energy and the final gravitational potential energy. So the way this works is we're going to assume that once this thing is infinitely far away, it's just barely moving, but it's moving so slowly that we're just going to say its kinetic energy is 0. Its final velocity is 0 and its final kinetic energy is 0. And it's infinitely far away, so we're going to say that its gravitational potential energy is 0. So we're kind of bending the rules a little bit and being flexible with our definition of infinitely far away to make this work, but that's what we do. So basically, we're going to start off with kinetic energy and initial GPE, no external work. At the end of this problem, so if we had 2 sketches, at the end of this thing is not going to be moving. It's going to be barely moving, but moving so slowly that we're going to ignore it. And it's going to be infinitely far away, which is technically impossible, but it's so far away that we're just going to call it infinity. So the right side is 0. So you take this, you do this, you solve this for v initial squared, and then you take the square root of both sides, and I replace the little I with a little e. So this initial velocity, well, this is what escape velocity is. So now we have an expression, a formula for escape velocity. So escape velocity is the square root of 2 times capital G times big M, so the mass of the planet we're leaving, divided by the radius of the planet. So let's actually apply this. What is the escape velocity of a 25 kilogram object on the surface of the Earth? So there I've given you the constant G. The mass 1 is going to be the mass of the object, 25 kilograms. There's the mass of the Earth, and there's the radius of the Earth. So something to point out right away. That's a red herring. In this formula, you have one m, and that m is the mass of the thing that is being escaped from. It is not the mass of the thing that's doing the escaping. The mass of the thing that's doing the escaping is not in the formula, so it has no effect. So you plug in the things, and you get this number, 11,180 meters per second. So bloody cheetah, that's about 11,000 meters per second. Well, that's about 22,000 miles per hour. That's really fast. And the other thing to point out about this number, 11,180 meters per second, you might remember this from the last part of the slides. So in the last part of the slides, we did this problem on the right side of this. So instead of starting with an object on the Earth and launching it so fast that it gets infinitely far away, we did sort of the opposite. We started with something, a 10 kilogram object, that was basically infinitely far away, and we just let it fall towards the Earth. So we started with the same formula, only this time we started with no kinetic energy. The thing wasn't moving. We were infinitely far away, so there was no initial GPE. There was no external work. And at the end, it had kinetic energy because it was moving, and it had GPE because now it was close to the Earth. And basically, you'll end up plugging in the same numbers. It looks a little different because we figured out the GPE in the previous part to this problem. But yeah, you get the same number. So nice little symmetry going on here. So if you launch something just fast enough from Earth so that it gets completely away and never comes back, you'll get this number. And if you start at infinity and drop something and just let it fall to Earth, when it gets to Earth, it would also have the same number. So neat the way the math works out. Unreasonably effective. So let's look at this formula, and we're going to think about the behavior of this formula, the behavior of this function, a math teacher might say. So if we're looking at this, 2 is a number, and g, that's the gravitational constant. Those numbers don't change. The m and r are variables. So look at this formula. What kind of value for m would make escape velocity go up? Would it be bigger or smaller? Well, it's in the numerator, so a big value for m would make escape velocity go up. Now, what kind of value for r would make escape velocity go up? So r is in the denominator, so that means when r gets smaller, your formula for escape velocity goes up. So what would happen if we had so much mass and so small a radius that the escape velocity from that radius was equal to c? And in physics and in astronomy, we use c to represent the speed of light. So what would happen if you had so much mass in such a small radius that the escape velocity from that radius was the speed of light? This would happen. This is an artist's rendition of a black hole. And I really wish we were all there in person so that you could all be asking questions and we could be talking about black holes. But 2020, it is what it is. So again, yeah, this is an artist's rendition of a black hole. When I first put these slides together years ago, we had no pictures of black holes. And then last year, we got this. So this is an actual image of a black hole. This is the black hole M87 star. 87, 81, I think it's M87 star. Yeah, so this is the supermassive black hole at the center of the galaxy M87. So, brief little overview of astronomy. So what is a star? A star is a very massive nuclear reactor. So when a star is alive, the astronomy students know this, a star is alive if it is performing nuclear fusion in its core. So while a star is alive, all of the mass of the star is trying to crush together under gravity. And in the core of the star, you have nuclear fusion pushing out. So gravity's trying to crush it, fusion's trying to blow it apart, and they're just in balance while the star is alive. So eventually, the star is going to run out of things that it can fuse, so it's going to lose this second thing. It no longer has nuclear fusion trying to blow it apart. It only has gravity trying to crush it. So very quickly, gravity is going to crush the whole thing down very, very small. So if we started with a big enough star, gravity is going to keep crushing it down and down and down, basically all the way down. It gets weird. So it's going to crush it all the way down until all of the mass is within a radius such that the escape velocity from that radius is the speed of light, which means that nothing, not even light, will be able to escape from within that radius. So, some things to point out. Most stars do not become black holes. Our sun, for example, is not going to be a black hole. Our sun is far too dinky of a star. For a star to become a black hole, while it was a living star, it has to have a mass of about 20 times the mass of our sun. And our sun only has 1 times the mass of our sun. So our sun's going to have a less interesting death. The sun's not going to blow up. It's going to become a white dwarf eventually, and it will shed its outer layers in what's called a planetary nebula. That's a different story. Take astronomy next year. I'll tell you all about it. But if you have a very massive star, about 20 times the mass of the sun, all of a sudden fusion ends and all of the gravity starts crushing the thing down, and very quickly it all crushes down. You get this giant supernova, and most of the mass that was there from this 20 solar mass star is going to get blown out into space. However, the core, so just, the heart of that star, if what's left has about 3 times the mass of the sun, gravity is going to keep crushing that part down, and nothing is going to be able to stop gravity from crushing it all the way down. So, for any kind of mass, this could be the mass, to be realistic, it should be the mass of a star, a fairly massive star, but really for any kind of mass, you can plug the mass into this formula, and, well, let me do it the other way. So here's our formula for escape velocity. Plug in c, the speed of light, for the escape velocity. So take c is equal to square root of all this stuff. Do the math, calculate r, and then we're going to give this r a special name called the Schwarzschild radius. I know it looks like Schwarzschild, but it's actually called Schwarzschild. So for any kind of mass at all, you can plug it into this formula, and you get what's called the Schwarzschild radius. So this is the radius to which, if you crushed that mass down to a sphere of that radius, you would have a black hole. So Schwarzschild radius, r sub s, kind of describes the size of the black hole. So at the center of a black hole, you have what's called the singularity. It gets confusing, but basically this is where all of the mass of the black hole actually is, which it's far more confusing than that, but that's the simple answer. So we're going to say all of the mass is here. 1 Schwarzschild radius away in every direction is really nothing. And then the surface, so the surface described by 1 Schwarzschild radius away from the singularity, is what's called the event horizon. So outside the event horizon, you're outside the black hole. Inside the event horizon, you're going down to the singularity. So nothing from inside the event horizon can ever leave. So a couple of things about black holes and a couple of misconceptions. So what would happen if you were just rapidly, so here's the sun, here's the Earth going around the sun, if you just walked right up and quickly flicked the sun out of the way and threw in a black hole that had the same mass as the sun. Now, again, the sun's not big enough to be a black hole, but let's just pretend that this were possible. So you just flick the sun out of the way and quickly swap in a black hole that had the same mass as the sun. What would happen? 2 things would happen. First thing is we would all freeze to death. It takes about 8 minutes from the light from the sun to get to Earth, so we wouldn't know that this had happened for about another 8 minutes, but then rapidly it would start to get really, really cold here. We wouldn't actually freeze instantly because there's heat trapped in the Earth and all that stuff, but we would freeze to death. The other thing that would happen would be basically nothing would happen. The Earth would just continue to go around this new black hole sun, which I'm not really a fan of the Soundgarden song. That's a different story. The Earth would just orbit that black hole sun exactly the way it did before. One of the misconceptions people have about black holes is that they're just like, I don't know, vacuum cleaners and just killing machines and annihilators. That's not really true. If you're far enough away from the black hole, things would just be normal. We would just do regular Newtonian calculations and figure out the Earth's orbit, and the Earth's orbit would stay exactly the same. Right now, we're going around the sun, and the sun is a big mass that we're orbiting. replace the sun with a black hole of the same mass, and we would just keep orbiting it. So if you're far enough away, it's just universal gravitation, Newtonian physics. It's when you get close to the black hole that things start to get really weird. So look here at the formula for the force due to gravity between any two masses. So imagine you're falling into a black hole and you're falling in feet first. So your feet would be very slightly closer to the black hole than your head were. In exactly the same way that if you're standing up, your feet are very slightly closer to the earth than your head is. Well, because your feet are slightly closer to the center of the black hole, your feet are getting pulled on with a greater force than your head is. Now, if you're far away, it doesn't make a big difference. But black holes are so massive that as you start to get closer and closer, that difference between the force between your feet being pulled toward the black hole and the force of your head being pulled towards the black hole starts to really matter. And you would start to get stretched out. And whenever you have this is called a tidal force, when the difference in the gravitational force across somebody is meaningfully different. This is called a tidal force. So what would happen in this case is you would get spaghettified. The technical term for this is spaghettification. You would get stretched out this way until you were not really a piece of spaghetti, like a long, thin piece of spaghetti. You would really be a long line of hot soup, basically. But we don't call it soupification. We call it spaghettification. Yeah, you'd get stretched out along this way. And again, I really wish we were all in class so that you could be asking questions and I could be drawing the little diagrams on the board about how this works. But yeah, we're not in class. So yeah, that's spaghettification. So I'll put a link to this Kurzgesagt video. This does a nice little summary of all the things I just talked about and how a black hole works, and also ultimately the fate of black holes, how black holes evaporate. And I'll also put a link to this video. So this guy explains what this image means. It's really complicated, this image. I know this video is getting long, so I don't want to go too far into it. But yeah, this is an image of a black hole. Watch the video. Basically, this black region here, it's not the event horizon. The event horizon would be closer inside there. This is what you would call the shadow of a black hole. It's complicated. Light is getting bent, gravitationally lensed. There's the photon sphere. It's a big mess. There's the accretion disk. There's this jet of stuff shooting out. It's all a mess. It's interesting stuff. If you take astronomy next year, I'll tell you about it. If you take physics too, I'll tell you about it in some detail. But yeah, interesting stuff. And that was new last year. Just about this time last year, this image was released. Basically, they did the impossible. They got an image of something that doesn't emit any light. It's really crazy. So to review, what goes up must come down. True or false? Yeah, that is false. If the object goes up with enough velocity, it's going to get away forever. It won't come back down. That velocity is the escape velocity. So speaking of escape velocity, what do you get when you have so much mass packed into such a small radius that the escape velocity from that radius equals the speed of light, 3 times 10 to the 8th meters per second? What you get is a black hole. So that's it for this part of the slides. If you, again, I'll put the links to the video in the description to my video here. If you have any questions, send me an email, a Google Hangout or something, or drop by my office hours. I'd love to talk about this stuff. Black holes are really, really interesting stuff. So hopefully you found this interesting.